Thank you very much. It's really my great pleasure and my honor to come to this summer camp. And so when I started preparing my lecture, I didn't know, the situation of the audience. So I guess I should prepare something a little bit technical. So in this context, I prepared, there are two presentations about two research papers that we recently finished with my PhD student. So, but let me know, I will mainly talk about the key ideas and some of the modeling techniques among these two papers. And let me know if you have any questions. We can stop anywhere because I think for each of the paper we have almost 1 hour to go through the content. So this leaves us plenty of room to discuss about the details. For the first session, I will introduce a topic about confounding models. I think among the audience, how many of you are working on traffic flow theory? Can you raise your hand? Not too many? Yeah, we have at least one. So confounding models is a kind of a very traditional or old-fashioned topic in transportation science or transportation engineering, because it's kind of one of the backbone model in traffic simulation. If you talk about vSIM, if you talk about Sumo, so there are basically two types of microscopic, behavior models, and there are confounding models, longitudinal models, and then later models, which is the lane changing models. And the confounding models have been widely used, in developing traffic simulation tools, and it has been long history. For example, the first generation we have the General Motors model, and then later we have something like Gibbs model, Forbes model, and Newell simplified model. And there are so many models already existed. But before implementing these confounding models into the computer, because actually confounding model is essentially a deterministic model. I have a deterministic equation for describing how people control the cars in terms of controlling the speed or acceleration. But before implementing any of this model into the simulator or into as a computer code, one thing I need to do first is to get the parameters, set the parameters of this model correctly, and then start your analysis. Because if you have wrong calibration or wrong parameters, the result you will generate will not be sufficient for you to do the analysis. So today I'm going to talk about one of the recent work, or two of the recent work we recently did about. We are trying to promote the idea of doing more like statistical calibration. We call it the Bayesian calibration. You will see what is the Bayesian concept afterwards of confounding models. And this is the joint work with my PhD student, Chengyuan Zhang. So let's get started. So before going into the topic, so let me talk about a few things about myself and where I'm working. So I'm now working at McGill University. So it's one of the university located in Canada. We are in the province of Quebec and the city of Montreal. So it's a French-speaking part of Canada, but McGill is an English-speaking university. And right now, we are a team in the civil engineering department, and we mainly work on transportation. So our lab is the smart transportation lab. So in the lab, we mainly do two types of research. So one type of research is on the methodological side. So on this side, we do a lot of the statistical modeling. So as you can see, from the talk presented by Sanjin today, so actually we do a lot of research on data analytics and spatial temporal data modeling. And you can see much of it is about how to develop efficient and effective statistical models or deep learning models to capture the complex correlation structure inside the data. So on this aspect, we work a lot on probabilistic modeling, Bayesian inference, Gaussian processes, uncertainty quantification. And we also work a lot on deep learning models, tensor decomposition, time series analysis, and so on and so forth. And in terms of applications, most of the methodology models we can develop in the first part can be used into 3 applications. So for the first application is about the integration with the intelligent transportation system. For example, the time series models we developed can be used as a efficient tool or effective tool for traffic forecasting. And the same applies to traffic data analysis, for example, traffic data imputation, travel time estimation, travel time prediction, and transportation network modeling, and emission modeling. So the other aspect is, about the probabilistic modeling side, or for example, the topic I'm going to cover today in the first session is about how to do stochastic traffic simulation. So this is a new topic we recently started to work on, because during the process of doing research on traffic flow, we realized that there's a lot of uncertainty has been ignored in the traffic simulation community, and then we are started to trying to promote to do traffic simulation in a more reasonable way, which is we refer to as stochastic traffic simulation. So then some of the methods we developed, for example, reinforcement learning. So this can be used to be integrated in tools or methods such as traffic control and management. So for example, some of the popular topics in reinforcement learning is in transportation is actually how to use reinforcement learning to control the traffic lights, right? And we have done some research about using reinforcement learning to control the operation of a bus fleet. And this is something unique from our group. So now let's get started. So what is the motivation? What is the motivation behind this line of work? So car-following models, as I stated in the very beginning, so it's a widely used, it's a kind of widely used model in macroscopic traffic simulation. So the idea of car-following model is, in fact, to simulate the behavior of a follower, which we refer to here as the blue vehicle. So here we have a time-space diagram. So y-axis is location, x-axis is time. So the two curves refers to the trajectory of the two cars. And we have a leading vehicle, which is in the red color, and then we have a follower, which is in the blue color. And the idea of car-following model is that given the information I provided you as a red curve, which is the trajectory of the leading vehicle, can you predict or can you estimate how the following vehicle will behave in response to the behavior of the leading vehicle? So then the whole idea is actually to extrapolate, given the red curve and given the partially observed blue curve, we try to extrapolate how the blue curve will evolve over time in response to this information. And physically, what we can perceive. So what are the typical input to the car-following models is essentially these 3 observations. We have S as a spacing, which is the distance you have in respect to the leading vehicle. And you have the speed for the current vehicle. For the blue vehicle, you have the current speed at time t. And if I compare the speed of the two vehicles at the same time, we have the delta V, which is the speed difference between the two cars. And the idea of car-following model is actually to estimate or to predict what is the speed or acceleration of the blue car should do at this instantaneous time point. So the goal of traffic simulation in the past, I think if we do engineering work, for example, using traffic simulation to evaluate, for example, whether this signalized intersection is properly designed, or whether the signal timing is properly timed, we can use traffic simulation tools, right, to see what is the overall delay at this intersection and how many cars are delayed per cycle, so on and so forth. So the goal of traffic simulation in the past has been, supporting this type of analysis. If I have a new design, I have a new project, can I use traffic simulation to, to visually, so one hand is visually evaluate, like what is overall performance, and then from the simulation result, we can also do some quantitative analysis to see, what is the overall delay, like in terms of and what is the queue length, for example, at the intersection. But with the development of the transportation sector or industry, you can see now people are started to use car following models or traffic simulation for more diverse types of tasks. For example, the development of autonomous driving vehicles. So before implementing these vehicles in the real world scenarios, normally what people have to do is to test whether these vehicles are okay in a simulation environment. And in that context, we have to develop, this kind of autonomous driving sector. One of the key research topics is even to use reinforcement learning to control the behavior of the vehicle in response to, surrounding vehicles and the environment. And in that context, we have to develop high fidelity simulation models to train the agent, to train the behavior of the your algorithm. And in that context, we will have to develop the high fidelity simulation model, right? And that high fidelity simulation model is still the traffic simulator we use for most of the case. We still use the traffic simulator we use in the first case to the engineering evaluation. For example, using vSim, AIM-SAN, and Sumo. And then people started to using the same set of simulation tools for reinforcement learning too, right? But the task becomes very different because in the first task, I'm trying to do some, policy evaluation or, implementation evaluation. So my overall result is to get the aggregated result, okay, in terms of delay, in terms of, queue length. But in the second context, in the future context, we are using this type of simulation models to evaluate, vehicle technologies, connected autonomous vehicles, reinforcement learning for traffic control and the management. And in this context, we started to wonder, is the existing traffic simulation model sufficient or enough for us to perform this kind of analysis or to perform this type of tasks? And the answer is, in fact, no, because as I said, most of the existing models are almost deterministic. And although there's a randomness in terms of how, what is the rate and when and where the vehicle enter into the network, but in terms of behavior part, it's mostly deterministic. But in the real world scenarios, for example, if we do development, if we try to develop some control algorithm for connected and autonomous vehicles, one thing we have to worry about is that whether my vehicle can perform well in the context of all the other drivers surrounding me are human drivers with some random behaviors. And in that context, we cannot believe the result we get from a deterministic simulation because the behavior of the human driver is hard to predict in certain sense. And one way to achieve this, to use old-fashioned car following traffic simulation to support this task is to introduce some randomness into the simulation. For example, we can introduce some random noise into the behavior of the physical model or car following model or lane changing model, and then using that simulation model extensively to evaluate. But to what extent that this simple strategy can reproduce reasonable behavior is hard to see. Most likely it cannot reproduce reasonable behavior. And the goal of this talk is actually we are trying to adapt our existing models. Our existing models is still there. We still trust these existing models and leverage these existing models. But the goal is simply to adapt these models a little bit and trying to make it capable of doing more realistic human driver car following model simulations. So in that case, we are interested in two questions we are trying to address. So one of them is how to calibrate a human driver car following model, given that the model is fixed, and how do we calibrate the parameters of these models? And then the second question is that given we have a well-calibrated model, how do we perform human-like car following simulations, or behavior extrapolations? So this is the motivation behind the talk today. And in terms of outline, I will introduce what is the backbone model we are going to use, which is the intelligent driver model, IDM, as an example. And then we will introduce two solutions, actually, to solve these two problems in terms of calibration and simulation. So, and then I will introduce some numerical experiment for calibration and simulation, and then I will get into the conclusion part. So let's start with the IDM model. So IDM model is a model proposed by Martin Traber and Doug Kelvin in 2000, which is not that old, but not that young either. And the idea of IDM model is that I still use the three covariates I have, which is the speed, relative speed, and spacing. And I try to model the acceleration of the following vehicle using this equation. So, and this equation, you can see, it has a closed form. It's an analytical equation. Given the three covariates I have, I can analytically compute what is the corresponding acceleration this car should take at a given time. And this model has a very parsimonious format, because as you can see from this equation, in addition to the three covariates, I only have 5 parameters, so which is the V0, S0, T, and alpha and beta, and this delta. So in general, we have 6, but given the identifiability issue, in most scenarios, we fix this delta to be 4, and we only calibrate the rest of the 5 parameters. So then the question starts to, with only these 5 parameters, can we really reproduce how people drive? The answer is clearly no, right? Because how people drive is a complex process. When we are driving the car, our brain processes information in the way that we perceive or we leverage information more than what can be modeled using 5 parameters, right? But for the simulation purpose, we make it simple. We make the model as simple as possible, as parsimonious as possible. But that also gets back to the question, because this parsimonious model cannot really reproduce how people drive in reality. So given this model we have, and the next question is about can we calibrate what are the correct parameters we should use in the simulation. So in this context, how do we do the calibration? Do you have any idea? So what type of data we should use? Travel time, Q length. All the trajectory data, right? So because car following model is essentially, trying to model this type of behavior. So one of the most straightforward data set I can leverage is relative trajectory data, trajectory data for a pair of vehicles. And then I can start using some simple techniques to do my calibration. So in the general case of the intelligent driver model, I can make an assumption that the real acceleration behavior is the acceleration produced by IDM plus a random noise term. And in that case, I can calibrate my, given the trajectories I can collect, I can calibrate the parameters of the IDM model by maximum likelihood. And then I just, given the trajectory I have, I assume that at each data point, at each time point, I have independent normal observations, with the mean produced by the IDM model and the variance with which another parameter I will introduce. And with that, I can get the, by applying maximum likelihood, I can get the file parameters as a result. And this actually corresponds to some of the loss functions in the literature. For example, in Panzo 2000, some of them have suggested to use this type of loss function. For example, trying to get a point-wise acceleration difference plus point-wise speed difference plus point-wise location difference. And if you look at the acceleration difference, the squared acceleration difference, this is exactly the maximum likelihood term in the general calculation. Okay, so now let's start with the calculation. So calibration. So for example, I collected some data and I tried to, so here I have 4 pairs of data. So each of this refers to field observation. So I collected some data and I started to get the true acceleration of the following vehicle, and I apply maximum likelihood to calibrate the parameters given this trajectory, and I try to use the calibrated model to reproduce or generate the corresponding acceleration from the model. So then we will get some result like this. So for each of the observation, I will see the black curve refers to the true acceleration curve, and the blue curve refers to the acceleration curve produced by the calibrated IDM model. So what do we see? So we can, in general, we can see the blue curve correspond to the black curve pretty well, right? The general trend is correct. So when the car should brake, the car is indeed braking. But one of the phenomena we observe across all the 4 examples is that if you look at the difference between the 2 curves, we will see, if I take the difference between the 2 curves and I plot it as this additional curve, I will see that the difference between the 2 curves also varies smoothly over time, which is small. Although the variance is small, but it also varies smoothly over time, right? So that is actually a very interesting observation. It's not surprising. So first of all, it's not surprising observation, but if you think about the way how we calibrated the IDM model, we are essentially assuming the error term to be independent, right? At each time point, the error term is independent. But if you look at the observed error or residue time series, it's a time series, so it's not independent, right? And this leaves us to the question that if I make this assumption that the error term is independent, and I use this independent term to do my calibration, to do my simulation, can I get the correct result? The answer is no, because our fundamental assumption is incorrect. So we are assuming something is independent, but then if we do the diagnosis, we found it's not independent. So IDM model can capture much of the variation, but there's still a lot of information. Some information still left in the residues, and the residues is not independent Gaussian distribution. We have to leverage some techniques to model this. So what do we miss? Essentially, what do we miss? So why there's a discrepancy between the two curves? So first of all, I think the reason is so clear that because IDM model is a parsimonious model, it's only 5 parameter, and the way we drive cannot be modeled by the 5 parameter. But in fact, there's a lot of physical reasons behind it. Because IDM model, as we can see, we only take the 3 covariate into consideration. There's not even braking light from the leading vehicle, right? But when we are driving a vehicle outside, I think people react heavily to the braking light of the leading vehicle. So if your model does not include the braking light into the vehicle, your model cannot generate a meaningful response from the followers, in particular in the emergency situations. And in addition to the braking light, there are various factors. For example, there's a reaction time from the driver. There's a difference. And when we are driving, sometimes we get distracted, and then our behavior is not stationary sometimes. And sometimes the driver drives in a more cautious way, and they try to even anticipate or predict what will happen to the vehicle in front of the leading vehicle, or several vehicles in front of you. And also there's some nudging behaviors from the follower, so on and so forth. There are so many factors that are causing that the IDM model to be incorrect or inaccurate in modeling driving behavior. So let's get into the solution part. So how do we integrate these factors when calibrating IDM? So then we started to think about the assumption we make. So I think one simple assumption is that to work on the assumptions. So in the general calibration, we are assuming statistical setting, we are assuming the error term to be identically and independent distributed following a normal distribution. But the true observation tells us the error term is series correlated instead of being independent. So what we can do is that we try to capture that effect. So instead of assuming the error term to be independent Gaussian, I can assume the error term to come from a temporal process or Gaussian process. And this is the decomposition we have. We still have the IDM term, but for the error term, I try to use this Gaussian process to capture it. So what is the Gaussian process? So Gaussian process is essentially a way to model stochastic process, and by using a kernel function. So the idea behind the Gaussian process is that for a collection of random variables, I can model them jointly as a multivariate Gaussian distribution with the mean function and also a covariance function. The covariance function, in most cases, we choose positive definite, or it has to be positive definite, and in most cases, we choose it to be a kernel matrix. And kernel matrix normally encode positive correlations. So for example, if I define a Gaussian process with a mean 0, a 0 mean, and the covariance function like this, if I sample from this Gaussian distribution, I will get some of the trajectories like this. So the green one is one sample, the orange one is one sample, the blue one is another sample. And in the kernel function, I can actually use the length, one of the parameter, which is called length scale, to control the degree, not the degree, but also the relative range of the correlation. So if I have a very large length scale, you can see the curve becomes very smooth. But if I put a smaller length scale, I can still sample from the multivariate Gaussian distribution, but I guess a smooth curve, but with many more fluctuations. This is a sample, for example, we can generate from a Gaussian process with length scale of 1 and length scale of 0.3 correspondingly. And then if I look into the difference between the IDM model and the true acceleration curve, I can see the relative difference, the residue curve looks like this. It looks very similar to what we can generate from a Gaussian process, right? So the shape looks very similar. As long as I have the correct length scale. So in this case, this two looks very similar, but this two doesn't look very similar. It means, so in this case, the length scale is too large to model this. So then the problem becomes, can we calibrate this model using this process? And then what we can do is that we assume the residual process follows a Gaussian process with a mean function of 0. And then I have to learn one additional thing, which is the covariance function or the kernel function. So that is essentially the whole idea behind this calibration framework. And in addition to this formulation, in the Bayesian context, I can also model driver heterogeneity, because if you think about each pair of trajectory, maybe for one pair of trajectory, I have the following vehicle as a big truck, or I have the following vehicle as a big bus, and I have a following vehicle as a Tesla. All these cars or vehicle driver combinations will produce very diverse behaviors. And it's essentially if I simply put all this data set into a single model, my model will be biased, because I cannot build one model which can model both trucks and Tesla, right? So I have to do an individual-based model. But if I want to do an individual-based model, let's leave some more questions, because we are using trajectory data to calibrate the model, right? And in order to calibrate the car-following model properly, so the driver has to take actions. For example, I have to get trajectory with strong reactions, braking, acceleration, so on and so forth. But trajectory data is so precious in the way that it only covers a very short range. Most of the trajectory data we have only covers like 20, 30, or 40 seconds to the maximum. And over this temporal range, 40 seconds, 30 seconds, to what extent can we observe the strong reactions from the follower is quite uncertain. So if we simply put this data set into an individual-based calibration, for example, if I simply take one pair of vehicle into the calibration framework, the result I get will be, sometimes I will be overfitting, because if the driver did nothing, just drive at constant speed over the 30 seconds, so then no matter what model you have, I only have one type of information. So I couldn't really, even my own model only have 5 parameters, I couldn't even calibrate that. So then the solution to this problem is called Bayesian hierarchical models. The idea is that I still want to capture the heterogeneity among all these vehicles, among all these drivers, but I can put a prior distribution which governs all the generation process. For example, each of the vehicle will have their own parameters, but it all jointly come from another distribution, which is we call the prior distribution. And in that sense, the only thing additional I have to do is to put some constraints on this prior distribution. If the prior distribution becomes very flat, then it corresponds to I'm calibrating model for each individual vehicle. For each individual vehicle, I calibrate a model. But I have the risk, in this case, I have the risk of overfitting. And the other solution is I have put the prior to be very sharp, to be a very narrow, very sharp distribution. And in that context, it corresponds to calibrate one single model for all the cars. Okay? And controlling the degree of the degree of variance in the prior distribution, I can actually properly characterize the heterogeneity among the drivers. So this is the idea, So by introducing a prior distribution, I can do individual-based calibration. But by controlling the variance of the prior distribution, I can achieve, both goals at the same time. So now let's get into the calibration part. So the calibration part is essentially the same. So I still use a likelihood-based calibration framework, but the only difference is that so in the general IDM case, I assume at each time point, I have a likelihood from a normal distribution, and everything is independent over time. And in the revised framework, in the memory augmented IDM framework, the difference is that for the whole trajectory, I build a kernel function, which is a covariance function. And I assume that over the whole trajectory, the acceleration comes from a multivariate Gaussian distribution. So this is a special case, actually. Multivariate Gaussian, like univariate Gaussian distribution, if we put them together, it's a special case of multivariate Gaussian distribution. Why is special? Because it refers to a multivariate distribution with diagonal covariance. And the difference we made here is that instead of assuming the covariance matrix to be diagonal, I assume we do have a kernel function with a proper length scale to capture the behavior. And let's get into the experiment. So in this case, we did experiment using the HiD dataset. We collected some pairs of car-following pairs. And the calibration procedure, as I said, just follow this Bayesian hierarchical model. And what we can get in the end is that we can see this two set of results I calibrated for Bayesian IDM with independent error assumption and Bayesian IDM with Gaussian process error assumptions. And if we compare this result, it looks very similar, but the problem is that if I assume the error term to be independent, I can see the error I have is very large because I attribute everything I cannot explain to the independent error term. But with our model, you can see the estimated error term becomes much smaller than that. And we can even get the correct length scale. If I put the length scale as a parameter 2, so for each of the car, I also calibrate what is the corresponding length scale parameters. So here our result shows the length scale is about 1.5 seconds. It means that when you are driving, probably you are taking into account the memory effect of probably 5 to 10 seconds. What you observe in the past 5 seconds probably all have an impact in the current behavior. So this is the visualization about the calibrated parameters, and we can see this way we can well reproduce the correlations, either positive correlations or negative correlation among some pair of the parameters. And now let's get into the simulation part. So now we can do proper calibration, but how do we do proper simulation? The idea is very simple. Since we have calibrated the model properly, the only task remains is to generate this random noise term properly, right? And in the general IDM case, we assume this random noise is independent. And I just sample random noise every time, and then I simulate my model. And in our case, we assume this random noise comes from Gaussian process. And I can do for Gaussian process, I can always do conditional sampling, And then what I get over time is a continuous trajectory. So now let's see what is the difference we can get from this type of two strategies. So it turns out that the difference is substantial because if we put everything into the random noise term, so the generated acceleration behavior will be almost looks like a random noise plus a mean term, right? But if we generate the random noise from the Gaussian process, what I can get from the acceleration curve is a collection of curves. So now you can see, so why it looks like cloud, because I generate a large number of samples. not only one. So basically here you have maybe 100 trajectories of the future behavior, and I plot them together. And if I generate these 100 acceleration trajectories, I simulate what is the corresponding location and speed, I can get the following two curves. So this is the speed curve of the following vehicle, and then this is the spacing curve in relative to the leading vehicle. And what we can see is that actually the traditional white noise IDM doesn't really perform very well, because if you see the discrepancy between the two trajectories, I can see there's a substantial discrepancy even in the very beginning. So which means that the true behavior cannot be even explained, even if you introduce randomness. But the distribution is generated from even like 10,000 examples, 10,000 samples, will not even cover what you have in the true observation. But with our case, with the memory augmented IDM, we can indeed achieve that. The black curve is well located in the distribution we generated from the red trajectories. So with that, we can even do uncertainty quantification to see how our model performs in relative to the stochastic simulation case. So I think later we also extended the same analysis to other covariance functions. So for example here, in the first generation of this model, we assume it's a Gaussian process. But if you look into the real-world trajectory data, the process we generate, the process we observe in the residue not only captures positive correlations, but sometimes they also encode negative correlations. And with that, one strategy we develop is to introduce a time series model, which is an autoregressive model to capture what is the structure or the shape of the residue. And I will not go into the details about this part, but the idea is essentially the same. In the GP part, I use the kernel function. But in the autoregressive part, what I can use is to use a simple autoregressive model for the process. And then my question becomes, for the first, I have to calibrate what is the kernel function. But in the second part, I have to additionally calibrate what is the parameters, what are the parameters of the autoregressive model. And the calibration process remains the same, but with the same data set, I can calibrate the model and reproduce, not only the positive correlation part, but also the negative correlation part. I think now let's get into the result. So with this new development, we also compared with the autoregressive model with the Gaussian process model. And from the probabilistic evaluation indicators, for example, RMSE and CRPS, we can see the autoregressive model essentially even outperforms the Gaussian process model. You can see this is the plot for the CRPS. CRPS is actually one of the indicators to show how good you are at uncertainty quantification. Because we are doing stochastic simulation, we want to ensure the uncertainty quantification, the probability distribution we generate is correct. And you can see the CRPS curve generated by the blue model, which is the autoregressive IDM model, is the best among all these models. So then I think we have demonstrated how to properly use these statistical models to do the simulation of one vehicle, right? But then what about the put a bunch of vehicles together, and then I ask all these vehicles to follow this kind of dynamic AR IDM models. So one experiment we did is to use the OpenACC dataset, which is a simulation of a platoon of vehicles. And as we can see, if we give all these vehicles specific parameters and then simulate, trajectories based on the error generation process, we can see our simulation can well capture what happens in reality, but in the end, what we get is a probability, is a distribution of trajectories instead of one trajectory. So we can simulate one scenario for 1,000 times, but that 1,000 times will give me different results. And by looking into this 1,000 results, I can get, to what extent I can capture the real behavior. And this is the simulation we did for multi-vehicle simulation on a circle road, for a ring road. And if we use a simple model, we can see we cannot really generate. So we can well capture the traffic dynamics in terms of the shock wave, but everything in addition to that looks rather homogeneous. But if we use our model with the stochastic simulation, we can see I can generate some very interesting and unique traffic phenomena. And that is actually pretty much everything I have for the first lecture. So the main takeaway is that driving behavior, there's a lot of uncertainty, but if we simply use the deterministic model and we code it into the simulator, I cannot trust the simulation result because I lose everything I have about stochasticity and uncertainty. And what we are proposing here is that I should do probabilistic simulation. So every time I should sample from a distribution in generating my trajectory. And some interesting observations from our analysis. So one interesting observation is that if we calibrate the model using Gaussian process, I can see that in most of the cases I can capture a correlation structure over 5 seconds. It means that when you are driving the car, what happens in the past 5 to 10 seconds all have an impact on your current driving behavior. So that also gives us the idea to develop some a more sophisticated model. For example, right now many research groups actually are proposing to, instead of using this parsimonious model, so I just put everything in a data-driven framework. I just put a bunch of trajectory into a deep learning model. And then I put a long sequence, maybe what happens in the past 30 seconds into the model, and then I train autoregressive model to get my current behavior. But our conclusion tells us, 30 seconds is probably too long, and 1 second or 2 seconds is probably too short. And our conclusion tells, you should probably put 5 to 10 seconds history, driving history into your model. And in that sense, you could have your best performed deep learning model, deep learning based autoregressive model. And the final conclusion is that IDM model is still a powerful model, but the only thing we miss in the literature is that we forgot the uncertainty part. But with the properly encoded uncertainty, I can do pretty much, very good traffic simulation in that context. So that's all I have for the first lecture. So you can see if there's any questions.
Yeah, I first comment because I used the simulation thermal before. I use its default car following model is IDF, and when I face a large scale simulation, it will slow down the performance. Yes. So if I use this car following model, how do you optimize it?
Oh, so that's a very good question. So you mean in a large-scale simulation, even the parsimonious IDM models is already becomes pretty slow, right? Because you are simulating too many vehicles at the same time. But we can have a look at what is the additional cost we have. Let's go to one of the equations we have here. Okay. So if you look at this equation, you will see what is the additional computational cost we have. after the model is calibrated. So this, the first term is IDM term, which is essentially you have calibrated IDM and you put into the equation, you get this term, right? So if I want to use this model to simulate Carponian model, to simulate Carponian behavior, the only requirement is that I need to, in the memory, I need to save not only the current information, but what I have in the past 1 second, 2 seconds, 3 seconds. But I save these 3 values, and I also save the 3 row parameters. And in total, I get one model. I get the same number of parameters, but I have to keep in the memory what is the past evaluation in the past sequence. And the calculation is essentially to combine them together. So you can see the only requirement is that in the memory I have to keep a small vector. So in the general IDM case I have a scalar, but now I need to take the IDM response. I need to save a vector of the past response, and every time I have to use a scan window to do my calculation. So, but in terms of efficiency, to me that is still a linear, computational cost. So that will not, bother too much in the computer.
Okay, thank you.
Thank you so much for my presentation. And my question is I think so from my aspect, this kind of concept can be not only implemented into the Carponian models, right?
Yes.
So I have because at the moment it suddenly comes to a concept like the social force models, also for the pedestrian trajectories and also crowd trajectories.
Yes.
So it could be parallel to this kind of.
Yeah, that's a very good question. So if you want to apply this model in a social force context, please go ahead. This is something I believe which is not done in the past, because the major question I talk about in the very beginning is that most of the people when they do simulation, they are still adopting the deterministic setting, right? So even in the social force setting, if I put everything there, so the movement of each individual person in the social force context is calculated as an equal sign. So here, I have your behavior equals to the result from the social force model, but result error. And in that case, as long as you have the same initial condition, the simulation will always give you the same result because there's no randomness inside. But instead, what you should observe in reality is that even if you provide the same initial condition, if you run the simulation multiple times, you should get different results because of the random part, which it cannot explain by the model itself because it's purely random. It's a random effect. And in that context, I can simply adapt this model framework into the social force model. Maybe I get a much richer, pedestrian simulation model. So the simulation cost is still the same, but I can generate, more diverse and more stochastic simulation behaviors.
Thank you so much.
Well, I think my question is similar with them more or less, but as far as I know, there are some types of a variation of IDM models, like the immense IDM model and some others. And do you think this methodology can be applied at the variation of IDM with the same concept and procedure?
I think so. So here we actually take I think the whole pipeline is we simply want to tell the story that we have to consider uncertainty in all these kind of simulation models instead of using a deterministic equation. No matter it's a more complicated IDM model or you have a simple chips model, no matter what model you have, this phenomenon will be always there. And I think the contribution we made is that the IDM part is not the key contribution. We can use any Carponian model here, but the reason we do IDM is that IDM behaves pretty well in almost all the general, carpooling simulation scenarios. There's no accident, and the driver's response is well captured by the equations. So then it provides us with a good opportunity to capture what is the unexplained uncertainty. And then our goal is actually to model this random noise term. So the IDM part is, we just want to keep it as simple but as comprehensive as possible. But it's not limited to IDM. I think any models can be used to be adapted in this statistical calibration framework.
I have one question.
Yes.
In the trajectory data, it's known to have many noise in there. When you apply this methodology, maybe that error term you train or you estimated may also estimate the noise. Is it?
Yes, that's very correct. I don't have it here, but actually in the paper, in these two papers, both available online, you can see our calibration is actually not based on this assumption. Because in the real world scenario, we don't really observe acceleration, because what we observe in the trajectory is only the location, right? At the location. So we have to do another layer. So transform this noise in the acceleration to the noise in location, and then plus the measurement noise in the location. And then in the end, we have to do something like a common filter in order to get the correct noise term in the acceleration. So in fact, this is what we did actually. In the calibration, because the acceleration is not even known from the trajectory data. So we have to use location data to calibrate the model. Thank you. Very good question.
Okay, so let's take a few minute break and can we start at 3:10?
Yeah.